Hello everyone. Today we are going to talk about hypothesis testing, a very crucial chapter in econometrics vis-a-vis statistics as a whole. Well, the potential values that a maximum likelihood estimator theta hat can take are unrestricted. Now the discussion is extended to determining if the population parameter has a certain hypothesized value, theta naught. If this value differs from theta hat, then by definition it must correspond to a lower value of the log likelihood function. And the crucial question is then how significant this decrease of the log likelihood function's value is. Determining the significance of this reduction of the log likelihood function represents the basis of hypothesis testing. That is, hypothesis testing is concerned about determining if the reduction in the value of the log likelihood function brought about by imposing the restriction theta equals theta naught is severe enough to warrant rejecting it. If, however, it is concluded that the decrease in the log likelihood function is not too severe, the restriction is interpreted as being consistent with the data and it is not rejected. The likelihood ratio test (LR), the word test, and the Lagrange Multiplier test (LM test) are three general procedures used in developing statistics to test hypotheses in log likelihood framework. These tests encompass many of the test statistics used in econometrics. They also offer the advantage of providing a general framework to develop new classes of test statistics that are designed for specific models. Suppose theta is a single parameter and consider the hypothesis where the null is theta equals theta naught and alternative is theta not equals theta naught. A natural test is based on comparison of the log likelihood function evaluated at the maximum likelihood estimator theta hat and at the null value theta naught. A statistic of the form is the log likelihood distribution form, where if we are looking into these on left hand side, we can see the distance between theta hat and theta naught illustrated by the vertical axis is the test which uses this measure in its construction is known as the likelihood ratio test. So likelihood ratio test is measuring the distance between theta hat and theta naught in a world test. In the distance theta hat and theta naught illustrated on the horizontal axis is an alternative measure of the difference between theta hat and theta naught. A test based on this measure is known as the world test. The Lagrange multiplier or the LM test is based on the measure on the gradient of the log likelihood function at the null value theta naught and the alternative value theta hat. The gradient at the maximum likelihood estimator, the GT theta hat, is 0 by definition. The LM statistic is therefore the distance on vertical axis or difference between the gradients of the parameters is LM statistics. So have a look into some of the null and alternative criteria. First, types of hypothesis: simple and composite hypothesis. If you are considering a model based on the distribution a function yt where the parameters are theta, the null and alternative hypotheses are given by if you have theta naught or theta 1, if your distribution or unknown parameter theta takes on theta naught and theta 1, any two values, then this is null and this is alternative, where theta naught represents the value under null and theta 1 is under alternative. Well, Both of these hypotheses represent simple hypotheses because as the parameter value in each case is given the distribution of yt under both the null and alternative hypothesis is fully specified. Now, on the other hand, if a hypothesis is constructed in such a way that the distribution of y cannot be fully specified, the hypothesis is referred to as being a composite hypothesis. So in a simple hypothesis, both of the distribution is fully specified. Under both null and alternative, the hypothesis is fully specified. In a composite hypothesis, the distribution of y is not inferred fully. The hypothesis is, that's why it's called composite hypothesis. Can be inferred fully. Distribution of y under null is not fully specified. Some of the parameters of theta are specified or can be inferred, remaining are not. So in that case, null equals theta, theta naught in one-sided test, theta equals theta naught equals theta naught. In alternative side test, theta is greater than theta naught or less than theta naught. In two-sided test. Okay, so let's move on from here. Okay, linear hypothesis is if number of k unknown parameters that equals beta 1 to beta 2 to beta k is k by 1 vector, m linear hypothesis to be tested simultaneously. The full set of m linear hypotheses is null r theta equals q and alternative r theta not equals q. R is m by k matrix and q is m by 1 matrix. Very important to remember that the dimension of the matrices. Now case 1 where k equals 1, m equals 1, or single, you see the number of parameters to estimate is just 1, where the parameter is beta, null is beta equals 0, alternative is beta not equals 0, which is LR test, likelihood ratio test. So how the degrees of freedom are represented by m, where we impose restrictions on R because the parameter that we are estimating will assume 1. The parameters we are not interested to estimate will assume 0, and Q remains 0 because Q is a m by 1 matrix. Q is simply the dimension of non-zero elements in the matrix. So there is just one parameter or one element, so Q is that. Then if you have two parameters, k equals 2, it's a m by 1 matrix, m equals 1, so unknown parameters are theta equals b1 b2. So we are testing one linear hypothesis, that's why it is 1, m equals 1. Null is beta 2 equals 0, alternative is beta 2 not equals 0. We are estimating, doing word test here. This is word test here. Interesting is that we are just measuring beta 2 out of the two parameters, not beta 1, the significance of beta 2, and hence R, which is our m by k matrix, we are imposing 0 for beta 1 because we are not testing for the significance of beta 1, and we are putting 1 against beta 2, the one we are estimating. Again, Q equals 0 because we are testing just one linear hypothesis. So the number of element that we are estimating is 1. Now in third case, where there are three variables, k equals 3, there are three parameters to estimate, and there's just one linear hypothesis. The parameters are beta 1, beta 2 and beta 3, where null is, when you add them up, they added together, null is 0, alternative is not equals 0. Because we are testing for significance for all three parameters, we impose put r against r equals 1 for all of them, but again, because we're testing for one linear hypothesis, so we are either we're jointly testing for if all of them the parameters are 0 or all of the parameters are non-zero. So Q again assumes one dimension 0, and in case of k is equal to 4, where you have 4 parameters and 3 linear hypotheses you are testing simultaneously, and you have 4 parameters, beta 1, beta 2, beta 3 and beta 4, where null is beta 1 equals beta 2. There are 3 hypotheses we are testing: beta 1, beta 2, beta 2 equals beta 3, beta 3 equals beta 4. Alternative is at least one of the restriction does not hold. What will be R? Interestingly, so beta 1 minus beta 2 equals 0, and first we are testing for out of the 2 parameters, one should be we are testing out of the 4, we are testing 2, so beta 1 minus beta 2, 1 minus 1, others we put 0 because we're not interested in the first hypothesis. For the others, and Q comes 0 for that first equation. Then the second linear hypothesis, where beta 2 minus beta 3 equals 0. So for beta 1, because we're not testing it, against beta 1 we'll put 0, against beta 2 we'll put 1, because beta 2 minus beta 3 equals 0, so the sign of beta 3 is minus. Then against beta 4 is 0. Beta 3 equals beta 4, or beta 3 minus beta 4, where the sign of beta 3 is positive, the sign of beta 4 is negative, so 0, 0, 1, minus 1. Now these restrictions arise in models of term structure of interest rate. We are going to use these when we are modeling the term structure of interest rate. Another case, when there are 4 linear hypotheses and 3 there are 4 parameters and 3 linear hypotheses, but null and alternative is a bit of different. When null remains same as number 4, but alternative is beta 1 equals 1 plus beta 3 minus beta 4. One of the restriction, at least one of the restrictions does not hold, is an alternative for alternative. So in null you have beta 1, beta 2, beta 2, beta 3, beta 3 equals beta 4, and beta 1 equals 1 plus beta 3 minus beta 4. That is something you are testing. In that case, again, for 1, 2 and 3, the first equation is beta 1 minus 1, 0, 0, then beta 2 equals beta 3, beta 3 equals beta 4. 0, 0, 1, minus 1, we understand beta 1 equals beta 2, and we understand beta 3 equals beta 4, but here is a bit confusion with beta 2 equals beta 3, because beta 1 equals 1 plus beta 3 minus beta 4. Alright, in that case we are concerned with beta 1 equals 1 plus beta 3 minus beta 4. The only difference with these from the previous equation is the last term, where beta 1 equals 1 plus beta 3 minus beta 4. So basically what we are doing here is that you see beta 3 minus beta 4 is beta 2 equals beta 3. So instead of beta 2, we don't need that parameter to estimate, because if we're estimating the parameter beta 3, we get beta 2. So beta 3 equals beta 4 is beta 3 positive 1 and beta 4 is negative. The sign of beta 4 will be negative 1. Rest we can just put zeros against. And finally, if you are taking everything for beta 1 for the equation beta 1 equals 1 plus beta 3 minus beta 4 on the left hand side, you see beta 3 assumes a negative sign and beta 4 assumes a positive sign, and basically we 1, there is nothing to put for 1, but because in these linear hypotheses there is a restriction that came with this imposition of 1, so we put 1 here in the dimension. Instead of zeros, we are using 1s here. That is something we need to remember. So if they are all equal, then that's not a problem. But if they're not all equal, like beta 1 equals 1 plus beta 3 minus beta 4, or taking everything on the left hand side, it becomes minus 1 minus beta 3 plus beta 4. So for that one, we put 1s here. That is something to remember. And in Q dimensions. Now this was in case of linear hypothesis. What happens if you have a nonlinear equation, where the full set of, in case of full set of M nonlinear hypothesis, given C theta is a M by 1 matrix of nonlinear restrictions, Q is M by 1 matrix of constants. So you have C, which is C theta is M by 1 matrix of nonlinear restrictions, Q is M by 1 matrix of constants. In case of C theta equals R theta, it's a linear case. Okay, so we were talking about R theta before. In case C theta becomes R theta, that becomes a linear case. So what are the cases? If null is beta 1 beta 2 non-linear, the multiplied equals 1, and alternative is beta 1 beta 2 not equals 1. You have two parameters, you have one nonlinear hypothesis to test, and the parameters are beta 1 equals beta 2 with C theta beta 1 beta 2, and Q is M by 1 matrix of constants. So you have one constant, Q equals 1. Why Q equals 1? Simply beta 1 equals 1 divided by beta 2. So you see, in that case you cannot impose restriction 0 on any of the parameters. You have to start with 1. So beta 2 can be, if you are measuring beta 1, beta 2 can be 1. If you are measuring beta 2, beta 1 can be 1. But you cannot put any 0. That's why we are dealing with 1s, not zeros. In another case, when k equals, there are two parameters, one non-linear hypothesis, and null is beta 1 divided by 1 minus beta 2 equals 1, alternative beta 1 divided by 1 minus beta 2 is not equals 1. The C theta restriction is beta 1 divided by 1 minus beta 2. Simply these type of restriction arise in dynamic time series models, where restrictions on the value of the long run multiplier are often imposed, and Q is 1. In 3 parameters, when there are two nonlinear hypotheses, you have 3 parameters, beta 1 beta 2 equals beta 3, and alternative is beta 1 divided by 1 minus beta 2 equals 1. What happens in C theta is simply, if we take everything on the left hand side, alternative is one of the restrictions does not hold, so the second equation remains same. There is nothing to be gained but 1, because we can only take 1 on the left hand side, and that 1, just like before, comes here on the second row of the dimension matrix Q, which is where 1s are located, which simply identifies which 1s are located. And for first one, it's simply 0, because we are dealing with only the parameters and nothing but the parameters. Likelihood ratio test. in case of a likelihood ratio test, theta naught is a restricted maximum likelihood estimator, theta 1. We are talking about two of the estimated parameters. Theta naught is restricted, theta 1 is unrestricted maximum likelihood estimator. If null is fully specifies the parameter, where null is theta equals theta naught, then the estimated parameter theta naught theta is also equals theta naught automatically. But in most cases, null will specify some of the parameters, leaving remaining parameters to be estimated to find theta naught. So generally, as we assume, estimated estimated parameter theta naught theta equals theta naught, or non-estimated parameter theta is also equals theta naught. And okay, so with log likelihood ratio test, we need to find log likelihood function of first theta naught, which is 1 by t, which is just the log likelihood function, simply 1 by t summation of log likelihood function of theta naught. And then you also need to find the log likelihood function of theta 1, and the general form of likelihood ratio test is simply minus 2t multiplied to log likelihood function of theta 1, which is the unrestricted maximum log likelihood, which is the estimator. No, I'm saying it other way around. Likelihood ratio test is minus 2t multiplied to log likelihood function of theta naught, which is the restricted maximum likelihood estimator, minus the unrestricted maximum likelihood estimation, or from the log likelihood function. So basically, the values of the log likelihood function of the restricted maximum likelihood estimator minus unrestricted maximum likelihood estimator. The difference multiplied to minus 2t is likelihood ratio test. As maximum likelihood estimation maximizes the log likelihood function, the term in the bracket is non-positive, marking a loss of probability. So if likelihood ratio test is between 0 to infinity, in that case, when likelihood ratio test is equivalent to 0, null is null. Null restrictions consistent, no serious loss of information is there, so we do not reject null. If likelihood ratio test is greater than 0, null restrictions are not consistent, there is loss of information, so we need to reject null. Very simple. So either the values of log likelihood ratio test should be equals or equivalent to 0 approximately, or not or simply greater than 0. If they are greater than 0, reject null, because there is a huge difference between restricted maximum likelihood estimator and non-restricted maximum likelihood estimator from the log likelihood function. Basically, there is a decrease in the log likelihood functions if they're greater than 0. The likelihood ratio test, the value of the likelihood ratio test is greater than 0. So we simply need to remember to reject null. Some examples, such as univariate normal distribution. In univariate normal distribution, the unknown parameters theta is mu and sigma square, and we know the log likelihood function, which is minus half log twice y minus half log twice sigma square minus summation of yt minus mu whole square divided by 2 sigma square t. Null is where mu equals mu naught. Alternative is mu naught equals mu naught, that is the test of mean. The unrestricted maximum likelihood estimators are mu1 equals the mean of summation of yt, or the mean of y, and sigma 1 whole square for the unrestricted maximum likelihood estimator, yt minus mean whole square and multiplied to the mean. So for unrestricted, we have the sample mean and the difference from the mean and observation, yt minus, instead of mu, is the sample mean, and we are taking the mean of it. So the log likelihood function at theta 1 is mu1 and sigma 1 square. So log likelihood function of theta 1 is half log twice pi minus half log sigma hat square, because it's estimated parameter, and simply exactly the same as yt minus mu hat. But here we have already shown in log likelihood function that the sample mean y bar equals the population mean mu hat. So yt minus mu hat is sigma square divided by sigma square, and they cross out, and log likelihood function at theta 1 remains just half. At the end of the log likelihood function, it remains half. So remember, this is unrestricted log likelihood function, this is restricted log likelihood function, restricted and unrestricted. The restricted maximum likelihood estimators are theta naught, the restricted, the parameter mean, estimated parameter mean equals the actual mean, and the sigma square is equal to yt minus mu hat whole square divided by t. And now the restricted maximum likelihood estimator, we have discussed here the unrestricted maximum likelihood estimator, where the last element becomes 1. In case of unrestricted maximum likelihood estimator, mu naught is equal to mu naught sigma square yt minus mu naught whole square, blah blah blah, and here the last term again becomes 1, because sigma square equals 1 by t summation yt minus mu whole square, same as this. So this one just crosses out with this one just crosses out with this, you see, including the t, so remaining with half. The likelihood ratio test is simply this parameter minus this parameter, and as we can see, we can do the math, and after doing the math, we are remaining with t log of sigma naught whole square, sigma naught square divided by sigma 1 square. Again, sigma naught is restricted sigma divided by unrestricted sigma whole square. So likelihood ratio test is distributed asymptotically at chi-square 1 as chi-square, where the p-value is 1 minus chi-square. Likelihood ratio test is 0 if it is 0 when both of restricted and unrestricted variances, the sigma square, they become equal. So when that's 0, we do not reject null. Otherwise we reject null because there is a loss of information. One of the variance is greater than the other variance. So this is something we need to remember. Multivariate normal distribution. If there is n dimension, and in case of there are dimensions are n and there are time is t, we have, in case of multivariate, 1 by twice pi to the power n by 2. In case of a matrix distribution, v half, well, v half is root over v, because 1 by 2 by n by 2 is n root over n. This is why this is, because we are actually taking root over. Just have a compare that with the single one. That was sigma square, right? And v is basically, we need to find the determinant of v. V is variance, so we're taking the root over of v and exponential of, because we need to take log likelihood, this will help us with that, exponential of half ut transpose and multiplied to ut, the residual, divided by v or v inverse, which is the multivariate variance. yt is n by 1 vector of dependent variables at time t. ut is yt minus bxt is n by 1 vector of disturbance with covariance matrix v. xt is k by 1 vector of explanatory variable covariance matrix v. xt is k by 1 vector of explanatory variable and b is n by k parameter matrix. The log likelihood function is 1 by t, simply the log likelihood function, which is minus n by 2 log twice y minus half log determinant of v minus 1 by 2t, summation of the disturbance in transpose and not in transpose multiplied to the inverse of v, which is the covariance matrix, with theta equals the parameter and the covariance matrix v. Consider testing m restrictions on parameter beta. The unrestricted maximum likelihood estimator of the covariance matrix v is mean multiplied to simply the disturbances, where the disturbance hat is yt minus beta hat multiplied to xt. Beta 1 is unrestricted parameter of beta. The log likelihood function evaluated at unrestricted estimator is the unrestricted maximum likelihood estimator of the covariance matrix, and the unrestricted estimator log likelihood function evaluated at unrestricted estimator is, well, bringing that down, because we have already seen that the covariance matrix equals the disturbances multiplied together and the mean. If we look into the equation, instead of the covariance matrix, we can jack in this information. After though they cross out, we have n by 2 log twice y minus half log determinant of v minus n by 2. Alright, or you can simply take common them in one bracket, which uses the result this. So summation of the last term equals trace of summation of ut covariance matrix ut transpose, or trace is actually the total number calculated. So what is trace? Very important. Trace is simply the summation of the diagonal elements of the covariance matrix. So here the last parameter we have two disturbance vectors multiplied to the covariance matrix. Here we are talking about the diagonal element, or simply trace t multiplied to when the, well, jacking in information from previously found equation. The covariance matrix is simply the disturbance vectors and its transpose multiplied and summed together. Multiplied together, we have t and tv. T is the total number of observations or the total time, v is the covariance matrix, and v inverse we already had, they cross out. So t multiplied to identity matrix, or tn. So trace is sum of diagonal elements. So now in this case, the restricted maximum likelihood estimator of the covariance matrix v is beta naught. Previously we are talking about v hat, beta v1 hat was unrestricted maximum likelihood estimator of the covariance matrix v. The restricted maximum likelihood estimator of covariance matrix v is v naught hat, which is again 1 by t multiplied to, now this time is vt hat and vt hat, where vt hat simply similar to the disturbance vector, we're just using v instead of u, where small vt hat is equal to yt minus beta hat xt. Now previously we had ut equals yt minus beta 1 hat xt. Now we have beta naught hat xt. Beta naught is restricted parameter of beta. Beta 1 was unrestricted parameter of beta. The log likelihood function evaluated at restricted parameter is n by 2 minus log beta naught minus 1 by 2t. Same as before, exactly same equation. And well, we have also considered this before, so minus 2t, likelihood ratio test is minus 2t multiplied to the difference between unrestricted and restricted. The first term is the restricted log likelihood function and unrestricted log likelihood function, and then simply because in both cases we have v0 and v1, the determinants of the covariance matrices for the unrestricted maximum likelihood estimator is v0 hat divided by restricted v1 hat. So in this case, in multivariate case, is t log v0 divided by v1, compared to in non-multivariate case it was t log sigma naught square divided by sigma 1 square. So unrestricted divided by unrestricted, v0, this is the determinant of the covariance matrix, divided by the determinant of the covariance matrix v1. That's all. Now there are some applications like Weibull distribution. An example, you have t equals 2 independent realizations, suppose, and the distribution is alpha beta yt to the power beta minus 1 exponential of minus alpha yt beta. This is Weibull distribution, we are already familiar with that. The parameters of alpha and beta. A special case of Weibull distribution is exponential distribution that occurs when beta equals 1. To test the data, draw from exponential distribution. Suppose null equals beta 1 and alternative beta not equals 1. So if beta equals 1, we have exponential distribution. The Weibull turns to exponential distribution. So we are testing for the hypothesis if our distribution is exponential or not. The unrestricted and restricted log likelihood functions are given as this: log alpha hat plus log beta hat. Okay, we are just taking logarithm of the Weibull distribution. First unrestricted, where there is nothing changed. Now in case of restricted, instead of beta we are using the parameter our hypothesized value 1. So we are restricting, we are not taking all the parameters, rather we are cutting off beta 1, because log 1 equals what? Log 1 equals 0. And putting in the values, instead of keeping the parameters, we do not use the parameter here in restricted case, the parameter beta. We remained with log sigma naught plus 1 by t summation of sigma naught y. So there is no b, no beta. This is the restricted compared to the unrestricted. And taking the two differences, log likelihood ratio test, Wald test. Another type of test is, well, the likelihood ratio test requires both restricted and unrestricted models. Wald test requires estimation of unrestricted models only, used when null estimation is complicated. So we just need unrestricted in Wald test, not restricted. So the Wald test is theta 1 hat minus theta naught transpose. Theta 1 hat is theta naught is restricted and unrestricted. Theta 1 minus theta naught, the true population parameter theta naught, and this is the unrestricted maximum likelihood estimator of the parameter theta 1 minus theta naught. Transpose and without transpose. In between we have inverse of the covariance of theta naught minus theta 1. Test statistics is distributed asymptotically as chi-square. M is the number of restrictions under null. The variances of theta 1 is, we are taking the covariance theta 1 minus theta naught. We are well, proceed going forward, well, the true population parameter is 0 for theta naught. It becomes simply the covariance, which is represented with omega theta naught divided by t. Now this can also be written as 1 by t omega theta naught divided by t, or 1 by t multiplied to information matrix, because we have already seen that somewhere. 1 by t equals multiplied to information matrix. Okay, now I remember where I have seen it. Basically, previously we have shown that summation of ut multiplied to ut transpose multiplied to inverse of the covariance matrix V. We are taking the trace of it, and V itself equals summation of ut multiplied to ut transpose. So V inverse in the case is multiplied to, instead of ut transpose we put V. V inverse V cross out, we have identity matrix In multiplied to T, because V is not equals ut transpose only, but it is ut multiplied to ut transpose divided by T. So we have T multiplied to the identity matrix. This is the exact same thing that we are putting in. Instead of the covariance theta naught omega theta naught, we are doing 1 by t identity matrix of theta naught. In case of Cramer-Rao lower bound inequality, the omega, the representation of covariance of the omega is greater than or equals 1 by the information matrix, the identity matrix of theta naught. Or this is the information matrix. Basically, information matrix theta naught equals inverse of negative Hessian, and negative Hessian is simply 1 by sigma square 1 by 2 sigma to the power 4. That's how we are getting sigma naught square by t. Just, you know, turn the numerator to denominator. That's all. We take it the numerator to denominator. For normal distribution, sigma naught square divided by t, 2 sigma naught square divided by 4, or the variance of mu and variance of sigma square. So asymptotic variances that this was found earlier, they represent asymptotic variances. Now we are gonna implement the test. To implement the test, the variance, the omega theta naught, is replaced by consistent estimator evaluated under null. The variance of the true population parameter is replaced with the variance of the but this is unrestricted, because there is no restricted in Weibull test parameter theta 1. So Weibull test is theta naught, theta 1 minus theta naught transpose, theta 1 minus theta naught transpose. We had V here instead of V inverse. Instead of V inverse, we can write 1t divided by omega theta 1, simply instead of V inverse, because V equals omega theta 1 hat divided by t. Compare theta 1 hat with theta naught. If theta 1 hat is approximately same as theta naught or converges to theta naught, voltage will be small. To determine significance, theta 1 minus theta naught is scaled by increase of pertinent standard deviation. So voltage helps us by giving us standard deviation. So we need to scale it. If voltage is small, then they could converge, which is expected for their significance. There is no loss of information. Another case is linear hypothesis. For Weibull test, we have talked about Weibull test with regular Weibull test. Let's check with linear hypothesis, where null is r theta equals q, voltage is r theta 1. So instead of theta equals theta naught, now we are talking about null r theta equals q, r theta 1 minus q transpose, r theta 1 minus q covariance is r theta 1 minus q inverse, where r theta 1 minus q can be written as covariance of r theta 1 actually, r theta 1 only because q equals 0 is a linear hypothesis. There's no 1 here, so q equals 0. Or instead of theta 1 hat, we can simply write the covariance divided by t, omega divided by multiplied to r transpose, right? Multiplied to r transpose instead of theta 1 parameter. We can write that. And yeah, on the wall test these two remains same, and so we jack in what we found here, r theta 1 hat multiplied to r transpose r omega theta 1 hat multiplied to r transpose. This is something we need to basically memorize because r theta equals q, so we basically need to memorize this. Okay. Asymptotically distributed with chi-square, where m is number of restrictions. M is number of restrictions. The first and last term remains same for all. In case of information matrix, t divided by r multiplied to r transpose multiplied to 1 divided by information matrix or inverse of information matrix in the denominator. Voltage with Hessian is simply negative of information matrix. Voltage is OPG or outer product gradient is simply again the inverse in the denominator. Then we are talking about normal distribution. In the normal distribution example, where null is equal to mu equals mu naught, alternative mu not equals mu naught respectively, with r 1 0, so we are just measuring one parameter, and q equals mu naught. The unrestricted maximum likelihood estimators are mu 1 and hat sigma 1 hat, where mu 1 is simply representing y sample mean, and sigma square is representing yt minus mu bar whole square divided by t, as we already know. And information matrix is 1 by sigma 1 square or 1 by 2 sigma 1 to the power 4. This is also shown before. So r theta 1 minus q equals y minus theta is r theta 1 minus k equals y minus theta. Or we can write r information matrix, or we can simply trying to see what it is. R information matrix inverse multiplied to r transpose. We are trying to solve this actually is equal to 1 by 0, 1 and 0. Now 1 and 0, this is x. Okay, so we need to remember this. We need to introduce these ones, what the restriction that is coming from 1 0 all the time. This is used in wall test. So this is simply the restrictions are simply the restriction, and this is coming from information matrix theta, which is 1 inverse. So theta minus q, r theta minus q. And what did we have for r and what did we have for q? Q is 0. R is because one parameter, we are estimating just one parameter, so 1 0 1 0 1 0 minus 0 0 is 1 0 1 0. That's all, very simple. And this one, they should equal to sigma 1 hat squared, or the variance. That's all. Voltage is hence t equals y minus sigma naught square divided by sigma 1 square. This form of voltage statistics is equivalent to square of standard t statistics squared of standard t statistics applied to mean of standard distribution. So we are applying standard t statistics on the mean and we are squaring the value that gives us the voltage value. Okay. If we are to look into non-linear hypothesis, for m linear hypothesis of the form c theta equals q, this is not linear. This is now we are talking about non-linear hypothesis. Alternative is say theta not equals q. World statistics is c theta minus q transpose. Well, r theta, instead of r theta everything will turn to c theta. And the covariance of say theta 1 inverse. Previously we have covariance in case of theta 1 minus theta naught inverse, where theta 1 minus theta naught later turned to 1 by d theta naught. So here the covariance is simply c theta naught minus q. Now c theta 1 transpose, sorry, c theta 1 inverse. Now computing covariance matrix c theta 1 inverse using delta method is covariance c theta 1 equals 1 by d theta naught omega theta naught and d theta transpose, in which d theta naught is equal to d c theta divided by d theta transpose. So the first difference of c theta for a normal distribution, when maximum likelihood estimator is theta hat equals the sample mean y, variance is sigma naught square divided by t, then c theta equals theta square, and the first difference d theta is equal to 2 theta and d theta naught is 2 theta naught. Standard error is hence of the sample mean is root over d theta square, because we have d theta multiplied to d theta, they turn to d theta square. This is the first difference of d theta and the variance of theta. So we have variance which is sigma naught square by t, and we have d theta naught which is 2 theta naught, and we square it up. So after that we just replace 2 theta naught equals sigma, we have what, we have 4 theta square, because 2 theta square, 2 square is 4 theta square multiplied to sigma square by t. This is substitution method result, or this is also known as the delta method. So let's look into our test with that. The first and the last element remains as it is, d theta added together. We have information matrix process, we have Hessian, and we have OPG. That's all. If restrictions are linear, where c theta equals r theta, then the first difference using c theta is not 2 theta naught, it becomes r, and these becomes the previous forms with linear hypothesis. And finally the last test, which is Lagrange multiplier test. Lagrange LM test is based on the property that gradient at the unrestricted maximum likelihood estimator, the gradient satisfied for the unrestricted parameter is 0, and that is the null. Alternative is the gradient is not equal 0. Generally the gradient is 0, as we know from previous chapter. And natural test statistics therefore to compute squared difference between the sample quantity under null, the gradient, and the theoretical value under alternative, and scale the result by increase of the covariance matrix, which is I theta naught divided by t. So basically gradient is 0, that is our null. So gradient minus 0 transpose minus 0 not transpose multiplied to 1 by the covariance matrix, 1 by omega naught theta naught, which is t by information matrix theta naught. Very simple. 0 0 is not there, so the gradient transpose and gradient t by I theta naught, that's all. So with information matrix this is this, with Hessian is simply negative Hessian, with OPG outer product gradient is simple this. Normal distribution, an example. In case of normal distribution, when null is mu equals mu naught, alternative mu naught equals mu naught, restricted maximum likelihood estimator is theta naught, where the parameters are this, and sigma in place of mu naught you can write mu naught. Okay, so as we were discussing, well, in case of normal distribution, the gradient on the other hand is simple. The gradient is simply the mean and the variance that we know from previous chapter, where mean we know here, well, in this case the first parameter, the first portion is simply yt minus mu square divided by, well, sigma square t, yt minus mu naught divided by sigma square t, which is the last element of the log likelihood function. First difference, last element of the log likelihood function. Then again the gradient evaluated at theta naught is minus 1 to sigma naught square. We are taking the difference again. If we take the difference the second time, this is what we are left with, first difference and the second difference. And basically we are just needing 1 minus mu naught. So basically, yeah, y minus mu naught, y by sigma naught square. So the first, this portion is what we are interested with. And the next portion, the second element, turns to 0. And the information matrix is simply 1 by sigma naught square 1 by 2 sigma naught to the power 4. This is also we have already learned. So 1 by sigma square 1 by 2 sigma 4. So Lagrange multiplier based on information matrix looks like this: 1 by sigma square y by y naught. So this one, y by y naught, mu naught divided by sigma naught square, inverse and without inverse, and in case of normal distribution, t divided by, you know, the information matrix. That's all. And then simply solving it, we have t y minus mu naught whole squared by sigma naught square. Okay, PV is chi-square distribution. You might need chi-square distribution for this problem. And then the next part is, yeah, chi-square distribution. Now that previous equation or normal distribution is distributed asymptotically as chi-square distribution. So it's similar to A, B is similar to A, which is the last one, with exponential distribution that is similar to the previous form, except for the two variants in denominator is based on restricted estimator mu naught square, where A is based on unrestricted estimator sigma 1 square. Okay, so this one is based on sigma naught square restricted, and the previous problem that we solved is based on sigma 1 square, which was before nonlinear hypothesis, when we were dealing with, you see, let me show you, sigma 1 square world statistics. Okay, so this is similar. The Lagrange multiplier has a similar structure to world statistics, except for, yeah, the normal distribution of world statistics, except for world statistics was based on unrestricted parameter, and Lagrange multiplier on the other hand is based on restricted parameter. Distribution theory. The asymptotic distributions of likelihood ratio test, Lagrange Multiplier, and Wall test under Null all have been stated to be simply chi-square, the asymptotic distribution of chi-square, where m is the number of restrictions used. Asymptotic distribution of Wall statistic. Here the crucial link to be drawn is that between normal distribution and chi-square distribution. The chi-square distribution of with m degrees of freedom is 1 by tau m by 2 multiplied to 2 m by 2 to the power y m by 2 minus 1 exponential of minus y by 2. This is the form. Consider the simple case of distribution of y equals z square, where z is n0, 1. Y is constrained to be positive because y equals z square. Z has its domain in entire line, while y is only positive domain. What that means, the inverse function is given by z equals plus minus root over y. Using change of variable technique, we can express probability distribution y in terms of z. Well, we have seen that if y equals fz dz by dy, where dz by dy or ddy of z, or the difference, first difference of z equals 1 by root over y plus minus, is the Jacobian transformation. This is called a Jacobian transformation. The probability of every y therefore has contribution from both negative z and positive z function. If y is a Jacobian, so for negative z minus root over y, for positive z plus root over y. Substituting the standard normal distribution will yield fy y root over twice pi exponential of minus z square by 2 with the determinant value of 1 by 2z plus 1 by root over twice pi. This is just putting things in to this equation, very simple. Okay, plus 1 by, so root over twice pi exponential of root minus z square by 2 and 1 by 2z, where here z's value is minus root over y, this value is plus root over y, or we can write y to the power minus root over 1 by root over y, or y to the power minus half by twice pi, root over twice pi multiplied to z square by 2, or this can be written as this. Okay, y by 2z is equal to root over y plus minus root over y. So tau 1 by 2 root over 2 exponential of this. The last step follows from property of gamma function. So this is the gamma function, where root over pi equals tau half root 2. This one remains what it is. Instead of z, we are putting this exponential of y by 2. And z square equals y. This is a chi-square distribution with m equals 1 degrees of freedom. For an example, we can use a single restriction case where null equals mu naught, alternative mu is not equals mu naught, tested by means of sample t statistics, where z is equal to mu minus mu naught, mu hat minus mu naught divided by sigma square, unrestricted parameter minus mu naught divided by sigma square multiplied to root over t. Lindbergh-Levi central limit theorem in chapter 2 suggests this under null it suggests that z square is distributed as chi-square, but from 4.4 the statistic z square is 2t root over mu by mu naught whole square divided by sigma square corresponds to Wall test of restriction. Wall statistics is asymptotically distributed as chi-square. Wall statistics is asymptotically distributed as chi-square. The relationship between normal distribution and t distribution may be generalized to the case of multiple random variable of where z1 is equal to zm or nm independent standard normal variables. The transformed random variables of y equals z1 squared to z square m is chi square m. So in case of multiple distribution, consider world statistic given in equation where this is the form we're already familiar with. Using Cholesky decomposition, it is possible to write this format R inverse R transpose divided by information matrix is SS transpose. S is a lower triangular matrix that has the property of SS transpose inverse if you're taking inverse of this or this. So S inverse transpose multiplied to S inverse. It is possible to write world statistics as W is equal to, in between we bring in Cholesky decomposition. Okay, Cholesky decomposition can be very easily called from MATLAB. Or this equals Z prime multiplied to Z, because this portion can be Z prime, this portion can be Z, equals is equal to 1 Zi square, where Z is equal to root T, S in transpose R theta 1 minus Q, 0 and mean and I information matrix distribution. So world statistics is chi-square distributed as chi-square M. So asymptotic relationship common test, we are continuing that world test statistics. So that is asymptotically distributed as chi-square under null. Suppose null is equal to theta equals theta naught is true, expanding log likelihood theta in second order Taylor series evaluated at theta equals theta naught will give us log LT theta naught is equal to log LT theta 1 theta naught minus theta 1. Okay, so we're dividing the whole thing into two parts, remember? Theta 1 minus theta naught gradient, theta naught minus theta 1 Hessian. Okay, so log theta 1 theta naught minus theta 1 gradient transpose half theta naught minus theta 1 Hessian multiplied to theta naught minus theta 1. So what is this actually? This is first portion is getting a bit well expanding through Taylor series, right? Okay, and previously we ended in W omega. So here log likelihood function theta naught equals theta 1 plus the portion of gradient plus the portion with Hessian in second order. So the gradient becomes this and the Hessian becomes the squared. Indeed, the remainder of Taylor series expansion is negligible as theta 1 at T consistent asymmetry of theta. So this is equivalent to these. Or now let's look into the Hessian part. Log likelihood theta naught equals theta 1 without gradient, because gradient turns to 0. So we are left with the Hessian part, and when we take difference or likelihood ratio test, we are left with T theta naught theta 1 theta naught theta 1 multiplied to Hessian, which is world statistics. This is the world statistics. So asymptotic distribution converges to world statistics. If we expand the gradient in a first order Taylor series expansion around theta evaluated at theta is equal to theta naught. So previously we proved in multiple restriction case world statistics converges becomes asymptotic. Okay, it's asymptotically they converge. The distribution of world statistics is asymptotic distribution with Cholesky. Expanding gradient in a first order Taylor series, we have theta naught is equal to, this is just the gradient portion, theta naught equals theta 1 plus Hessian, where theta 1 with unrestricted gradient is 0. We're left with the Hessian portion. Substituting this expression into Lagrange multiplier test, what do you have? We have Lagrange multiplier is T theta naught minus theta 1 theta naught minus theta naught theta 1 minus theta naught theta 1 minus theta naught. In between you have Hessian divided by Hessian, and as we move down as both restricted and unrestricted Hessian parameters are asymptotically equivalent under null. No matter what we use in terms of asymptotic distribution, they converge. Even these Lagrangian multiplier converges towards statistics. So previously we told that likelihood ratio statistics converges towards statistics asymptotically. Lagrangian multiplier statistics converges to statistics asymptotically. Wow, that's very interesting. When it is easier to estimate unrestricted model by world, Lagrangian multiplier test is the most or Lagrangian multiplier world test is the most common to compute, most convenient to compute. In case of finite sample relationship, finite sample distribution of test statistics is unknown and commonly approximated by asymptotic distribution. If asymptotic distribution does not provide an accurate estimate, second order approximations are based on first order Taylor series expansion of the gradient. We have seen already. For better accuracy, higher order expansion using Edgeworth expansion is better. Number 2, Monte Carlo method. Simulate finite sample distribution for t and compute corresponding critical values from simulated values. Transformation. Transform the statistics so that the asymptotic distribution provides a better approximation. For example, distribution of correlation coefficient, which is asymptotically normally distributed, although convergence is relatively low. In terms of who rejects null more frequently, worst statistics rejects null more than likelihood ratio. Then likelihood ratio rejects more than Lagrange multiplier. If sigma unrestricted variance is less than the restricted variance, world statistics is greater than Lagrangian multiplier statistics. In terms of who rejects null. Now, size of test. The probability of rejecting a null hypothesis when it is true, or we are talking about type 1 error, is usually denoted alpha. Level of significance or size of test. If alpha is 0.05, null is rejected for probability value that is less than 0.05, or test. This is type 1 error. So rejecting null when we should not reject null is type 1 error. And if alpha is 0.05, we reject null when the probability value is less than 0.05, or test statistics fall within rejection region. Size equals probability of world test. In simulation, the size is computed by simulating the model under null when restrictions are true and comparing the proportion of simulated values are greater than critical values obtained from asymptotic distribution. Cascodem 0.05. Simulated size is equivalent to asymptotic distribution if simulated size is greater than critical value. This is oversized. If simulated size is less than critical value of Cascodem, this is undersize. So if in case of undersize, null rejects less often than predicted by asymptotic distribution. In case of oversize, null rejects more often. And we use this simulated value compared to that to critical value, and we see if this allows us to understand if our simulation size is oversized or undersized. Computing, for example, computing tests of hypotheses where null is equal to beta 1 0, alternative beta 1 not is equal to 0 is exponential regression model, in which exponential beta naught beta 1 x parameters are beta naught beta 1, computing size by simulating 100,000 times under null. The world statistics, for each the world statistics is this equation. I think we will do this problem. Power test. The probability of rejecting the null when it is false is called power of a test. Type 2 error is when we fail to reject null when it is false. So power of a test. Like before, simulate under alternative. Proportion of simulated value is greater than critical value. If proportion of simulated value is greater than critical value, then it is approximately power of test. and then we think we should be using, probably will use this. And in this case, power of full test beta 1 is 0 is 0.05. The size adjusted, so power of test increases, the size adjusted power of test, you see, increases monotonically. It is increasing after 0 as the value of beta moves further away. Maximum power of 99% attains at plus minus 4 maximum power of the test. So as t increases, power increases, power of the test increases. That proves that it's a consistent test. So this is where the theoretical part ends. Next we will talk about MATLAB.